Let's do two more examples where we're asked to find the most general antiderivative. I'm given f of x equals tangent squared x. And I think about the formulas on page 283, and I think about all the antiderivatives I've seen, and I haven't seen anything about tangent squared. But I look through that table on page 283, and I do see a formula involving a secant squared. Well, I remember that tangent squared x plus 1 is secant squared. That's a Pythagorean identity, which would tell me that tangent squared x is secant squared x minus 1. So I can use that identity to rewrite this in terms of secant. And now, because of my linearity rules, I can just find the antiderivative of both parts. The antiderivative of secant squared is tangent. The antiderivative of 1 is x plus an arbitrary constant c. All right, well, we can check our work by differentiating, and you will get secant squared minus 1, and then we'd have to apply a trigonometric identity to get back to tangent squared. In number 2, I'm given q of x equals a polynomial divided by x, and again, no rule I'm comfortable with right now would help me find that antiderivative. But I could imagine rewriting q of x by doing all of the division. And now I have 1, 2, 3, 4 terms, all of which are easy to antidifferentiate. So q of x, big Q of x, the antiderivative would be 1/5 x to the 5th minus 4/3 x cubed minus 2x plus 3 times the natural log of the absolute value of x plus c. And again, we could check our work by differentiating. We will get this back, and then a common denominator gets us back where we started. So the moral of this lesson is that sometimes we might have to do a little bit of trigonometry or a little bit of algebra to give ourselves an easier statement to find an antiderivative of.